Okay, so today's learning objective is a really big one. We're trying to put together a lot of your key skills so far. So, in learning objective 1, you were learning about position and position versus time graphs, which is part of the learning objective today. In learning objective 2, you were learning about velocity and velocity versus time graphs. You also learned a little bit about acceleration in learning objective 2-2. And then in learning objective 2-3, you were learning about free body diagrams. And you can see in this learning objective 2-5 that we're putting all of that stuff together. We're learning to relate graphs of position, velocity, and acceleration versus time to free body diagrams. All of this hinges upon one of Newton's 3 laws. The way you learned Newton's first law in junior high school was you learned that objects in motion tend to stay in motion. And objects at rest tend to stay at rest unless acted upon by an outside force. Now, that's a decent way of thinking about it, and we can use it to understand some basic situations. One of those basic situations is right here. We have an air hockey puck. That air hockey puck is an object in motion. And since it does not experience any outside forces like friction, because it's floating on air, the air hockey puck will continue in motion essentially forever until it hits the side, right? So an object in motion tends to stay in motion is a useful idea here. Here we have a coffee cup that is at rest on top of Mr. LaForge's car. And I can tell you numerous times that I've made this exact mistake where this coffee cup is at rest. And so it will stay at rest when the car starts to move. And then, of course, it'll, fall down because of gravity. But, once again, a useful application of Newton's first law, the way it was stated in junior high school. But in high school, we're going to state this law a little bit differently. It's the same thing, but it's a little bit more specific as far as the wording. So we're going to say that objects move at constant velocity. If you think about it, that's actually the same thing that you said in junior high. Objects in motion stay in motion. Well, that's constant velocity. And the unless part is going to be unless they experience not an outside force, but what we call a net force. Basically, an outside force makes it sound like there's only one force at a time. Net force is a technique we use to account for all the different forces on an object and figure out if those forces are actually going to change the object's motion and take it out of constant velocity. Okay, so that's what we're saying. Objects move at a constant velocity unless they experience a net force. Now you might say, and students often do, that, well, I'm sitting here in my desk and there's no force on me. So why am I not at constant velocity if that law is true? Well, I want to remind you that first of all, if you zoom out, you'll realize that, well, yes, you're sitting there, quote unquote, not moving, but you're actually on top of something that is rotating at a speed of 1,000 miles per hour. And not only that, but it's flying through space, going all the way around the sun every single year. So while you might be or seem to be at rest compared to all the things around you when you're sitting in a chair, you're actually moving at constant velocity, and really everything is always moving at constant velocity. And that's what Newton's law is about. Everything moves at constant velocity. The only way to change that is with a net force. So now we need to learn what a net force is. A net force is when the forces in one direction are greater than the forces in the opposite direction. Sorry, I already said direction there. I don't need to type that again. And whenever the forces are greater in one direction than in the opposite direction, the net force is measured as the difference between those forces. Okay, so let's use some examples. Here we have two forces, and they are in opposite directions. Those two forces are equal, and so in this case, there is no net force because there's no difference between those forces. In this case, we have two forces that are in opposite directions, but they are not equal, and so there is a net force. And the net force is equal to the difference between those forces. 3 minus 2 is 1 Newton. We also have to show the direction of that net force, because net force is a vector, just like all forces. And so it has not only a magnitude or an amount, but it also has a direction. So in this case, the net force is 1 Newton up. In this situation, we have two forces that are opposite each other, and they are equal. So in that direction, there is no net force. But this force has no force opposite to it, and so it is greater than its opposite force. And in this situation, there would be a net force of 2 newtons to the left. In the last situation, we have two forces that are opposite, and they are equal, and so there is no net force. And in this direction, we have two forces that are opposite and equal, and so there is no net force in that direction either. So overall, this is no net force. Notice that it doesn't matter that this is 2 newtons and that's 3 newtons, because they are not opposite from each other. All right. So that's what a net force is. Remember, objects that have a net force do not move at constant velocity. They accelerate, while objects that do not have a net force will move at constant velocity. So let's just actually use some color highlighting real quick. This is no net force, and so it would be constant velocity. This object has a net force, and so it would accelerate. This object has a net force, and so it would accelerate. And this object has no net force, and so it would move at constant velocity. Now, we don't know how fast the objects will move. We don't know what direction they will move. These diagrams just don't show us that. But we do know whether they accelerate or move at constant velocity. Okay. Now, since this learning objective is all about connecting forces to motion graphs, I want to do a quick review of motion graphs and how to identify it. So the first thing when we're talking about motion graphs is that we must remember each motion graph is different. And so whenever you see a motion graph, you have to slow yourself down. You have to look at the the slope, and think about the slope's units in order to figure out what the slope means. For example, on a position versus time graph, slope is velocity. Okay, so notice this is a position versus time graph, and the slope is velocity. Now, how do I know that? Well, I would come over here and look at the units of the y and the x-axis. This is meters, this is seconds. So if I'm finding the slope, the units of my slope are going to be meters for the rise and seconds for the run, which gives me a slope unit of meters per second when I do rise over run. You should realize that this unit is the unit of velocity. And so the slope of this graph is the velocity. Okay? And that's true of all of these position graphs. The velocity for this one, and this one, all of those slopes are the velocity of the graph. Now, what can those velocities do? Well, the velocity can be doing a lot of things, and I've actually written them down here. And it's all based on what a slope can be. So the slope, or the velocity, can be positive, and it can also be negative. And I want to attach that to some of these graphs down here. So for example, in this graph, the slope is positive. And in this graph, the slope, or the velocity, is positive. Now, in this graph, the velocity, or the slope, is negative. And in this graph, the slope, or the velocity, is negative. The other thing that it can do is it can be 0, like it is in this graph right here. That's 0 slope, and therefore 0 velocity. The object is not moving in that situation. Also, the velocity can be increasing, and it is in this situation. You can see that the slope gets greater, it becomes greater, and so this object is increasing its velocity or accelerating. Also, the slope can be decreasing, which it is in this one. You can see that the slope gets less and less as time goes on. And then lastly, the slope of a position versus time graph can be constant. And the slope here is constant. So it's constant velocity. The slope here is constant velocity. And the slope here is constant velocity. Okay? Now, what part of that do I look at when I'm thinking about forces? Well, if I'm looking at any of these with a constant velocity, that is going to be no net force. And if I'm looking at any of these with a changing velocity, that has to have a net force. Okay? Down here, when we look at a velocity versus time graph, the rules are very different. So again, we're going to look at the units of the y and the units of the x. We're going to realize that when we find slope, it's going to be the y unit over the x unit to create a slope unit of meters per second, which is sometimes written as meters per second squared. That unit is the unit of acceleration. And so the slope of a velocity graph is not velocity. That wouldn't make any sense. The slope of a velocity graph is the acceleration of the graph. You should know that already, but this is just hopefully serving as a review of those things as we try to put all these big ideas together. And we want to realize that as we look at these slopes, the acceleration or the slope of this graph can be positive. And we'll add that up here as well. Or it can be negative, like it is in this graph over here. Or it can be 0, like it is in this graph right here. Now, again, how does this relate to forces? Well, if the acceleration is 0, there is no change in speed. We're moving at constant velocity. And so there would be, in this case, no net force. Whereas on the other ones, when the acceleration is where the velocity is either increasing with a positive acceleration, or the velocity is decreasing with a negative acceleration, those situations would require a net force. Okay, so if you know what a net force is, and you can look at a motion graph and determine if a net force is required, you are doing a great job in a very difficult unit. So